Picture this: you're floating in the emptiness of space, staring into the gaping maw of a cosmic monster so powerful, it warps the very fabric of reality around it. Light bends, time slows, and the laws of physics as you know them begin to unravel. This isn't science fiction. This is the edge of a supermassive black hole, lurking at the heart of our galaxy and countless others, an invisible titan with gravity so strong, not even light can escape its grasp. And yet, these enigmatic giants hold secrets that could rewrite our understanding of the universe itself. What if I told you that supermassive black holes aren't just destructive voids, but cosmic architects shaping the fate of entire galaxies? Or that they might hold clues to some of the biggest mysteries in astrophysics, from dark energy to the birth of stars. Today, we're diving headfirst into the abyss to uncover 30 mind-blowing secrets about these gravitational behemoths, secrets that will challenge everything you thought you knew about space, time, and the forces that govern our cosmos. From the shocking way they're born to the eerie whispers of their collisions across billions of light years, supermassive black holes are anything but silent monsters. They hum with energy, spin at unimaginable speeds, and even blast jets of matter at nearly the speed of light. Some are ancient, older than the stars themselves. Others are surprisingly playful, hurling stars across galaxies like cosmic pinballs. And here's the wildest part: we're just beginning to scratch the surface of their mysteries. So buckle up. By the end of this journey, you'll see these cosmic titans not as terrifying voids, but as the universe's most fascinating storytellers, holding tales of creation, destruction, and perhaps even the future of our own galaxy. Here's the astonishing truth: our Milky Way galaxy, along with nearly every other large galaxy in the universe, harbors a hidden monster at its core. These aren't just any black holes, they're supermassive giants, some weighing in at millions or even billions of times the mass of our Sun. To put that into perspective, imagine squeezing all the matter from 4 million suns into a single point so dense, it warps space and time around it. That's the scale we're dealing with when it comes to Sagittarius A, the silent behemoth lurking at the center of our own galaxy. But how do these cosmic titans end up anchoring entire galaxies? It all comes down to gravity. Their sheer mass bends the fabric of space-time so dramatically that stars, gas, and even other black holes are drawn into their orbit like moths to a flame. Over billions of years, everything near a galaxy's center gets pulled into this gravitational whirlpool, feeding the black hole's insatiable appetite. Yet, despite their terrifying power, supermassive black holes don't just consume. They shape the destiny of the galaxies they inhabit. Their gravitational pull orchestrates the motion of stars, funnels gas into swirling accretion disks, and even triggers the birth of new stars in distant spiral arms. What's truly mind-bending is the sheer range of these monsters. Some, like the one in our Milky Way, are relatively modest by supermassive standards, a mere 4 million solar masses. But then there's the record holder, Ton 618, a black hole so colossal it dwarfs our Sun by 66 billion times. That kind of mass creates a gravitational influence stretching across thousands of light years, bending the paths of stars and warping the very structure of its host galaxy. Even more intriguing, these black holes aren't just passive anchors, they're active participants in the life cycles of galaxies, sometimes flaring up with enough energy to outshine every star around them. So next time you look up at the night sky, remember, hidden in the heart of our galaxy, a silent giant is shaping the cosmos in ways we're only beginning to understand. The sheer scale of supermassive black holes defies comprehension, so how do these cosmic titans grow to such mind-boggling sizes? Imagine a monster that starts as a mere seed, perhaps a remnant of an early massive star, and over billions of years balloons into something with the mass of billions of suns. It's a process as violent as it is fascinating, driven by 3 main cosmic buffets: feasting on gas, cannibalizing smaller black holes, and possibly even tapping into the invisible grip of dark matter. Take gas for starters. Picture a swirling whirlpool of superheated material spiraling toward the black hole's event horizon in what's called an accretion disk. This isn't some orderly cosmic conveyor belt, it's a chaotic, high-energy maelstrom where friction heats gas to millions of degrees, creating blinding quasars that can outshine entire galaxies. Every time a black hole gorges on this cosmic banquet, it grows heavier, its gravitational pull tightening like a noose on the surrounding space. But gas isn't the only thing on the menu. When galaxies collide, a slow-motion dance lasting hundreds of millions of years, their central black holes eventually lock into a deadly spiral. Like two sumo wrestlers circling each other, they merge in a cataclysmic event that sends ripples through space-time itself. These gravitational waves, first detected in 2015, reveal just how often black holes engage in these cosmic wrestling matches. Some grow so massive they become unstoppable, like the monster in galaxy M87, weighing in at 6.5 billion solar masses. And then there's the wild card, dark matter. While we can't see it, this mysterious substance makes up 85% of the universe's mass. Some theories suggest black holes might grow by trapping dark matter in their gravitational web, slowly absorbing its invisible energy. It's a tantalizing idea, one that could explain how the earliest supermassive black holes grew so big, so fast in the young universe. But here's the kicker: black holes don't just eat endlessly. They're messy diners. Some meals trigger violent outbursts, jets of plasma shot out at near light speed, clearing entire regions of gas and effectively putting themselves on a cosmic diet. It's a self-regulating cycle of feast and famine, with each black hole writing its own violent autobiography across the stars. And as we peer deeper into the cosmos, we're finding these growth spurts are more than just random events. They're the hidden engines shaping galaxies themselves. There's an invisible line in space where the universe as we know it ends, the event horizon. Think of it like standing at the edge of the most powerful waterfall imaginable, where the current becomes so strong even light gets swept away. Once something crosses this boundary, there's no climbing back out, no signal sent home, not even a final cry for help. It's the ultimate point of no return, where the black hole's gravity wins forever. But what makes this boundary so strange isn't just its power. It's how it warps our understanding of reality. Time itself behaves differently here. To an outside observer, an object falling toward the event horizon appears to slow down, frozen in place like a paused video. Yet from the perspective of the doomed traveler, time flows normally as they plunge past the threshold in an instant. This eerie effect, called gravitational time dilation, means two people could experience the same event in wildly different ways, one watching for centuries, the other feeling only a heartbeat. The event horizon isn't a solid wall or a fiery barrier. It's more like the moment a spaceship's engines fail while escaping a planet's gravity, except here, the planet is a black hole and the escape speed exceeds the speed of light. That's why nothing, not even photons, can break free once they cross over. Yet, paradoxically, black holes aren't the cosmic vacuum cleaners we once imagined. They don't suck matter in like a drain. Instead, objects follow the natural curves of space-time, much like planets orbiting a star, until they stray too close to that invisible edge. Here's where it gets even weirder. The event horizon isn't just a one-way street for matter. It's also a mirror of sorts. Quantum physics suggests that information about what falls in might not vanish entirely. Like a scrambled message, it could linger on the surface, encoded in ways we're still struggling to decode. This idea, known as the holographic principle, hints that everything swallowed by the black hole might leave a ghostly imprint on its edge, a cosmic receipt for the universe's most destructive transaction. So while the event horizon marks the death of anything that crosses it, it's also a laboratory for the most extreme physics imaginable. It's where Einstein's relativity clashes with quantum mechanics, where time bends until it breaks, and where the universe seems to keep its deepest secrets just out of reach. And as we peer closer with telescopes and simulations, we're realizing this mysterious boundary isn't just the end of the road, it's a gateway to discoveries that could rewrite the rules of reality itself. Crossing the event horizon might mean vanishing forever, but the journey there is anything but peaceful. Imagine being pulled feet first toward a black hole while your head lags behind, stretched thinner and thinner like a strand of cosmic pasta. This horrifying transformation isn't science fiction. It's a real phenomenon called spaghettification, where tidal forces near a black hole rip objects apart atom by atom. The culprit is gravity's brutal gradient, the difference in pull between your feet and your head. On Earth, the effect is too minuscule to notice, but near a black hole, gravity's grip is so intense that even a few feet of distance can mean the difference between surviving and being shredded. Picture a loaf of bread stretched into a single, impossibly long noodle, except instead of dough, it's an entire star or planet being unraveled. Astronomers witnessed a preview of this carnage in 2019 when a black hole in a distant galaxy devoured a star. Telescopes caught the star's final moments as it was torn into a luminous stream of gas, swirling into the abyss like water down a drain. The process is horrifically efficient. First, the star balloons under intense heat, then gravity's invisible hands yank it apart, stretching it into a glowing ribbon before swallowing it whole. Even spacecraft wouldn't stand a chance. A human astronaut venturing too close would experience every molecule in their body pulled in different directions, bones, muscles, even the spacesuit itself elongating like taffy until nothing recognizable remained. It's a fate far worse than burning up in a star or freezing in deep space. It's the universe's most extreme form of torture, turning solid matter into cosmic thread. Yet this violence isn't just destructive, it's illuminating. The light from spaghettified stars reveals secrets about black holes themselves, like their spin and mass. As matter stretches and heats up, it emits X-rays and radio waves that telescopes can analyze, turning gruesome deaths into valuable data. So while spaghettification spells doom for anything caught in its grip, for scientists, it's a flashlit glimpse into the dark heart of the universe's most enigmatic monsters. The glowing halo around a black hole isn't just for show. It's a cosmic pressure cooker where matter meets its doom, radiating energy so intense it can outshine entire galaxies. This luminous ring, called an accretion disk, forms when gas, dust, and even stars spiral toward the black hole's event horizon, squeezed into a swirling maelstrom of superheated plasma. Temperatures here soar to millions of degrees, turning the disk into a beacon visible across the universe. Think of it like water circling a drain, except instead of a gentle whirlpool. It's a frenzied vortex where friction and magnetic fields churn matter violently. As particles collide at near light speed, they release energy across the electromagnetic spectrum, from radio waves to deadly X-rays. It's this radiant fury that allows astronomers to spot black holes even though they're otherwise invisible. The accretion disk acts like a neon sign in the cosmic void, screaming, "Here be monsters." Some of the brightest objects in the universe, quasars, are powered by these disks. Imagine a single accretion disk so energetic it can blaze brighter than 1,000,000,000,000 stars, a lighthouse shining from the edge of time itself. But not all disks are created equal. The size and glow depend on the black hole's appetite. A dormant giant like Sagittarius, a star in our Milky Way, has a faint, sputtering disk because it's starved of material. Meanwhile, active black holes in galaxy cores, like the one in M87, feast so greedily their disks glow white-hot, jetting out plasma beams that stretch for thousands of light years. What's truly astonishing is how much these disks reveal. By studying their light, scientists can measure a black hole's spin, mass, and even its magnetic personality. The disk's inner edge, for instance, hugs the event horizon so tightly that its flickering patterns map space-time itself, twisting under the black hole's grip. Sometimes the disk hiccups, flashing in erratic bursts as magnetic fields snap like rubber bands, flinging material into space. These tantrums give us clues about how black holes grow and how they sculpt their galactic homes. So while the event horizon marks a point of no return, the accretion disk is where the action happens, a chaotic, radiant stage where matter takes its final bow before vanishing forever. And for astronomers, that glow is more than just light. It's a Rosetta Stone, translating the silent language of black holes into something we can see, study, and begin to understand. At the heart of a feeding black hole, something extraordinary happens. Twin beams of plasma erupt from its poles at nearly the speed of light, carving through galaxies like cosmic blowtorches. These aren't just random bursts of energy, they're relativistic jets, some of the most powerful particle accelerators in the universe, stretching tens of thousands of light years into the void. Imagine a fire hose of supercharged gas, hot enough to vaporize entire solar systems, blasting outward with enough force to sculpt entire galaxies. These jets are born from chaos. As matter spirals into the black hole's accretion disk, intense magnetic fields twist and snap like rubber bands, channeling some of the infalling material away from the event horizon. Instead of vanishing forever, this plasma gets catapulted outward along the black hole's spin axis, achieving velocities so high that time itself slows down for the particles inside them. The result, a dazzling, high-energy beam that can punch through interstellar gas, creating shockwaves visible across millions of light-years. Their impact is staggering. When these jets slam into surrounding gas clouds, they trigger shockwaves that compress material, sparking the birth of new stars like a cosmic domino effect. In some cases, they act as galaxy-scale regulators, heating up surrounding gas so thoroughly it can't cool down to form stars at all. This push and pull dynamic explains why galaxies with active supermassive black holes often have fewer young stars. Their jets literally shut down stellar nurseries. But here's the twist: these jets might also be cosmic gardeners. By distributing heavy elements forged in the accretion disk's inferno, they enrich distant regions of space with the building blocks for planets and life. The iron in your blood, the calcium in your bones, could trace back to material hurled across the cosmos by these particle cannons billions of years ago. Perhaps most mind-bending of all is how long these jets persist. The one erupting from galaxy M87, captured in the first ever black hole image, stretches 5,000 light-years, a testament to sustained energy output that dwarfs anything humanity could muster. And when two galaxies collide, their black hole's jets can entangle, weaving intricate patterns of energy visible in radio telescopes. Far from being random eruptions, these jets are precision instruments, fine-tuned by the black hole's spin and magnetic personality. Some flicker like cosmic strobe lights, others remain steady for eons. But one thing's certain: they prove that black holes aren't just destroyers. They're cosmic engines shaping the universe on scales we're only beginning to comprehend. Black holes aren't just cosmic vacuum cleaners, they're cosmic whirlpools, spinning with such ferocity that they drag the fabric of space-time along for the ride. Picture a giant sinkhole, not just pulling water down the drain, but twisting the entire bathtub around it. That's what happens when a black hole rotates, warping reality into a swirling vortex where time and space lose all meaning. Some of these monsters spin at nearly the speed of light, their rotational energy so immense it can power jets of plasma stretching across galaxies. Measuring this spin isn't just a technical challenge, it's like trying to clock the speed of a tornado while standing inside it. Astronomers can't directly observe a black hole's rotation, so they rely on indirect clues like the flickering X-rays from its accretion disk or the way its gravity bends light. The disk itself holds critical hints. The faster the spin, the tighter the inner edge hugs the event horizon. In extreme cases, a rapidly spinning black hole can fling matter outward like a slingshot, creating erratic bursts of energy that light up telescopes across the universe. But why does spin matter? Because it dictates how a black hole interacts with its surroundings. A sluggish rotator like Sagittarius A star quietly sips on nearby gas. But a fast-spinning giant becomes an engine of destruction and creation. Its rotation generates powerful magnetic fields that launch those relativistic jets, shaping star formation thousands of light-years away. Even stranger, a spinning black hole can serve as a cosmic time machine of sorts. Near its edges, frame dragging, where space-time itself is pulled along, could theoretically slow or speed up time for an outside observer. Here's the kicker: some black holes spin so fast they defy physics as we know it. The theoretical maximum, called the Kerr limit, suggests a black hole can't rotate faster without revealing its singularity, a breakdown of Einstein's equations. Yet, tantalizing evidence hints that a few might be pushing this boundary, spinning at over 99% of the speed of light. If confirmed, it would mean these objects are even more bizarre than we imagined, twisting space-time into knots we've yet to unravel. So while black holes might seem like silent giants, their spin tells a violent, dynamic story, one where gravity doesn't just pull, it dances, and in that dance they rewrite the rules of the cosmos itself. Not all black holes are created equal. While supermassive monsters dominate galactic centers, their smaller cousins, stellar black holes, lurk in the cosmic shadows, born from entirely different catastrophes. The difference isn't just about size, it's about origin, behavior, and the way they shape the universe around them. Picture a grizzly bear standing next to a house cat, both predators, but with vastly different footprints on their ecosystems. Stellar black holes form from the dramatic deaths of massive stars. When a star 20 times heavier than our Sun exhausts its nuclear fuel, it doesn't fade gently, it collapses in a supernova explosion so violent that the core implodes into a singularity. What remains is a black hole typically 10 to 20 times the Sun's mass, crammed into a space smaller than a city. These compact killers usually roam isolated regions of galaxies, occasionally revealing themselves by siphoning gas from a companion star. Now contrast that with a supermassive black hole. These behemoths weigh millions to billions of solar masses and didn't form from a single star's death. They likely grew from ancient seeds in the early universe, perhaps primordial black holes or collapsed gas clouds gorging on galaxies worth of material over billions of years. Unlike stellar black holes, which scatter like cosmic nomads, supermassive black holes anchor entire galaxies, sitting firmly in the center like gravitational monarchs. Their impacts couldn't be more different. A stellar black hole might bend the path of nearby stars or create a flickering X-ray binary as it nibbles on a neighbor. But a supermassive black hole, it orchestrates the dance of billions of stars, heats galactic gas to millions of degrees, and can even halt star formation across entire galaxies with its relativistic jets. Yet here's the strangest twist: despite their size gap, these black holes share eerie similarities. Both warp space-time, both have event horizons, and both follow the same fundamental laws of physics. The universe just scales them up or down like cosmic Russian dolls, and sometimes they even work together. Stellar black holes occasionally spiral into supermassive ones, creating gravitational waves that ripple through the cosmos. So while stellar black holes are the universe's precision knives, small, sharp, and lethal in close quarters, supermassive black holes are the wrecking balls, reshaping galaxies with their sheer gravitational might. One represents the end of a star's life, the other the heartbeat of an entire galaxy, and together they show us just how versatile darkness can be. The early universe was a place of chaos and extremes, a time so alien that even the laws of physics as we know them seemed to bend under the pressure. Yet in this primordial soup, barely 700 million years after the Big Bang, supermassive black holes already existed. That's the cosmic mystery baffling scientists today. How did these gravitational titans, some weighing billions of times the Sun's mass, form so quickly? The universe simply hadn't existed long enough for them to grow through normal means, like gobbling up stars or merging with smaller black holes. So what's the answer? Astronomers are racing to solve this puzzle, and their best theories sound like something from a science fiction epic. One leading idea is direct collapse, a scenario where enormous clouds of pristine gas, untouched by heavier elements, simply imploded under their own weight. Picture a cosmic shortcut, bypassing the usual star formation process entirely. These clouds, dense and cold, could have collapsed directly into black holes with masses tens of thousands of times our Sun's, seedlings for the supermassive giants we see today. Unlike black holes formed from dying stars, these primordial monsters would have had a head start, born already massive and hungry. Supporting this theory are recent observations of distant quasars, shining with the brightness of 1 trillion stars, powered by black holes that shouldn't have had time to grow so large. But there's another possibility. The first generation of stars, called population 3 stars, might have been unlike anything we see today. Made purely of hydrogen and helium, these stars could have been hundreds or even thousands of times more massive than our Sun, cosmic behemoths that burned bright and died fast. When they exploded as supernova, their cores may have collapsed into black holes far larger than typical stellar remnants. Over time, these black holes could have merged or devoured gas at astonishing rates, snowballing into the supermassive monsters we find in young galaxies. The most radical theory, though, involves cosmic inflation, the rapid expansion of the universe moments after the Big Bang. Tiny fluctuations in density during this period might have created regions so dense they pinched off into black holes immediately, without needing stars or gas clouds at all. These primordial black holes, if they existed, could have served as the seeds for galaxy-spanning giants. What's clear is this: the early universe didn't play by the rules we're used to. The formation of supermassive black holes in such a short time frame challenges our understanding of physics, forcing us to rethink how structure emerged from the primordial fireball. And with every new discovery, like the recent detection of a supermassive black hole dating back to when the universe was just 5% of its current age, we're reminded that the cosmos has a flair for the dramatic, crafting impossibly massive objects in the blink of cosmic time. Imagine a beacon so bright it outshines 1 trillion stars, visible from the farthest edges of the cosmos, an object so luminous that its light has traveled over 13 billion years to reach us. This isn't a hypothetical scenario, it's the reality of quasars, the universe's most dazzling powerhouses, fueled by supermassive black holes in their most ravenous states. These cosmic lighthouses are more than just brilliant anomalies, they're time capsules, offering a glimpse into the universe's violent adolescence when galaxies were young and black holes feasted with abandon. At their core, quasars are active galactic nuclei gone wild. When a supermassive black hole gorges on gas, dust, and even stars at an extraordinary rate, the material doesn't vanish quietly. Instead, it's funneled into an accretion disk so energetic that it glows brighter than all the stars in its host galaxy combined. Friction heats the disk to millions of degrees, blasting radiation across the electromagnetic spectrum. From X-rays to radio waves, while magnetic fields twist and snap, launching those signature relativistic jets we see stretching across cosmic distances. The result, a quasar, a pinpoint of light so intense it can drown out entire galaxies in its glare. What makes quasars truly remarkable isn't just their energy output, it's their role as cosmic mile markers. Because light travels at a finite speed, the farther we look into space, the further back in time we see. The most distant quasars detected existed when the universe was less than 1 billion years old, a mere fraction of its current age. Their existence so early in cosmic history poses a tantalizing question. How did supermassive black holes grow so massive so quickly? Some quasars from this era harbor black holes weighing billions of solar masses, objects that, by conventional models, shouldn't have had enough time to form. Their very presence forces us to rethink the universe's early growth spurts, suggesting mechanisms like direct collapsing gas clouds or voracious feeding rates we've yet to witness in the modern cosmos. Yet quasars aren't just relics of the past, they're also key players in galactic evolution. The energy they unleash can heat surrounding gas to such extremes that it stifles star formation, effectively putting the brakes on a galaxy's growth. In this way, quasars act like cosmic regulators, their outbursts shaping the destiny of their host galaxies for eons. And while most quasars today have quieted down, their black holes transitioning to less active states, their legacy lingers. The heavy elements forged in their accretion disks were spewed into the cosmos, seeding future generations of stars, planets, and perhaps even life. For astronomers, quasars are more than dazzling oddities, they're tools. Their light, filtered through intervening gas clouds, reveals the composition of the universe's large-scale structure. Like a flashlight shining through fog, quasars illuminate the cosmic web's hidden filaments, the vast, invisible network of dark matter and gas that connects galaxies across the void. And occasionally, when a quasar's light passes close to another massive object, gravitational lensing magnifies and distorts its image, offering a natural telescope to probe details otherwise too faint to see. So while the era of peak quasar activity has passed, their light still guides us. They remind us that even the darkest objects in the universe, black holes, can become the brightest beacons, etching their stories across space and time for any civilization curious enough to look up and wonder. At the heart of our Milky Way, hidden behind thick curtains of dust and gas, lies a sleeping giant, Sagittarius A star. Unlike the ravenous quasars blazing across the early universe, this supermassive black hole is surprisingly tame, more like a lazy cat curled up at the center of our galactic home. Weighing in at 4 million times the mass of our Sun, it should be a cosmic terror, yet it emits barely a whisper of energy compared to its more active cousins in distant galaxies. This quiet demeanor has puzzled astronomers for decades. Why isn't our black hole feasting on the abundant gas and stars swirling around it? The answer might lie in its dining habits. It's not that Sagittarius A star isn't hungry, but rather that it's a picky eater, consuming material in erratic, small bites instead of the gluttonous feast seen elsewhere. Then, in 2022, humanity finally got its first real look at this enigmatic neighbor. The Event Horizon Telescope, a global network of radio observatories acting as one Earth-sized dish, captured an image of Sagittarius A star's shadow, a glowing ring of light bending around the event horizon's darkness. The image was fuzzy, yes, but monumental. For the first time, we could see the gravitational monster anchoring our galaxy, its silhouette matching predictions made by Einstein's equations over a century ago. The resemblance to the earlier image of M87's black hole was uncanny, proving that these cosmic titans follow the same rules no matter their size or temperament. But Sagittarius A star still guards its secrets closely. Its quiet periods are occasionally interrupted by bizarre flares, sudden bursts of X-rays and infrared light that brighten its accretion disk for hours before fading again. Some theories suggest these flares happen when passing stars or gas clouds stray too close, ripping apart in tidal dances that briefly wake the giant from its slumber. Other clues come from the bizarre orbits of nearby stars like S2, which whips around the black hole at blistering speeds, its path tracing the invisible grip of gravity so strong it redshifts light just by existing. Perhaps the most startling realization is how gentle Sagittarius A star has been with its galactic neighborhood. While other supermassive black holes blast their surroundings with deadly radiation, ours sits relatively peacefully, allowing stars and life to flourish in the Milky Way spiral arms. It's a cosmic paradox. The same force that could shred planets into spaghetti also seems to be a quiet guardian. its gravity organizing the galaxy while rarely flexing its full destructive power. Yet don't mistake its calm for weakness. If a massive gas cloud or star cluster ever wandered too close, Sagittarius A could awaken in a spectacular display of cosmic violence. For now, though, it remains a silent sentinel, a reminder that even the universe's most fearsome predators can sometimes doze, letting the galaxy spin on undisturbed. Black holes don't just live at the centers of galaxies, they shape their destinies. Imagine a cosmic thermostat capable of turning star formation on or off across an entire galaxy with nothing more than a whisper of energy. That's the staggering influence of supermassive black holes, whose gravitational pull and explosive outbursts regulate the birth of stars in ways we're only beginning to understand. Take galactic winds, for example. When a black hole feeds, it doesn't just swallow material quietly. It belches out colossal gusts of superheated gas, racing outward at millions of miles per hour. These aren't gentle breezes, they're hurricane-force tempests powerful enough to sweep entire star-forming regions clean of gas. Picture a gardener ripping up seedlings before they can take root. That's what these winds do to future stars. The mechanism is brutal but efficient. By ejecting the raw material for star formation, the black hole effectively hits the pause button on its galaxy's growth. But winds are just one tool in the black hole's arsenal. Those relativistic jets, the ones shooting plasma at near light speed, act like cosmic blowtorches, carving through interstellar clouds and heating them to temperatures too high for stars to condense. In some galaxies, like the nearby Messier 87, these jets stretch for thousands of light years, creating vast bubbles of scorched gas where star formation has been snuffed out entirely. It's a paradox. The same black holes that devour matter can also sterilize their surroundings, preventing new stars from ever igniting. Yet not all black holes are destroyers. In a twist of cosmic irony, their very destruction can pave the way for creation. Shockwaves from jets and winds sometimes compress surrounding gas just enough to trigger new star birth at their edges, like a wildfire clearing the way for fresh growth. Some galaxies even show rings of young stars, perfectly aligned with the black hole's outbursts, a testament to its dual role as both executioner and midwife. The scale of this influence is mind-boggling. In massive elliptical galaxies where supermassive black holes are particularly active, star formation often grinds to a halt entirely, leaving behind a quiet sea of aging stars. Astronomers call this quenching, and it's one of the universe's most dramatic examples of feedback, a delicate balance where the black hole's growth curtails its own fuel supply. Too active and it starves itself, too quiet and gas accumulates, reigniting star formation. It's a self-regulating cycle that's shaped galaxies for billions of years. What's truly humbling is realizing how interconnected these systems are. The same black hole that could vaporize a solar system in seconds is also a galactic architect, its outbursts echoing across millennia. Without these titans, galaxies might never have taken the forms we see today, their spiral arms, bulges, and halos all sculpted by the invisible hand of gravity's most extreme manifestation. So the next time you gaze at a galaxy, remember, its beauty isn't just the work of stars and gas. Behind the scenes, a silent giant is pulling the strings. Stephen Hawking once dropped a bombshell on the physics world, a paradox so troubling it shook our understanding of reality to its core. Imagine tossing a book into a fireplace. The pages burn, but the information, the words, the ideas isn't truly lost. It lingers in the smoke, the ashes, the heat radiating outward. But toss that same book into a black hole and the rules change. According to Hawking's calculations, black holes don't just swallow matter, they erase information itself from the universe, violating one of quantum mechanics' most sacred laws. That information can never be destroyed. This is the black hole information paradox, a puzzle that sparked decades of debate. rewired theoretical physics, and even forced scientists to question whether Einstein's relativity and quantum mechanics can ever truly coexist. At the heart of the paradox is Hawking radiation. Black holes aren't completely black, they slowly leak energy, evaporating over unimaginable timescales. Hawking showed that this radiation is thermal random, featureless, like the static from an untuned radio. The problem: if the black hole eventually vanishes, leaving behind only this meaningless noise, what happened to all the information about the stars, planets, and gas it consumed? Quantum mechanics insists that information is preserved always. It can be scrambled, hidden, or encoded, but never erased. Yet Hawking's math suggested black holes do exactly that, wiping the universe's hard drive clean. The implications are staggering. If information truly vanishes, it means the universe has a fundamental case of amnesia. History isn't just written by the winners, it's being shredded by black holes. This sent physicists scrambling for solutions. Some, like Leonard Susskind, proposed holography, the idea that all the information swallowed by a black hole isn't lost but smeared across its event horizon like a cosmic etch-a-sketch. Others, like Gerard T. Hooft, suggested black holes might spit information back out in subtle quantum twists, hidden in the Hawking radiation itself. Then there's the radical firewall hypothesis, which claims the event horizon isn't a smooth gateway but a searing wall of energy that fries anything touching it, preserving information by preventing it from ever entering the black hole in the first place. The debate is far from settled. Recent breakthroughs, like the discovery of soft hair, tiny quantum imprints on a black hole's surface, hint at possible information storage mechanisms. Meanwhile, labs are simulating black holes using ultra-cold atoms and holographic models, testing these theories in ways nature never could. What's clear is this: the paradox isn't just about black holes. It's a proxy war between relativity and quantum mechanics, two pillars of physics that refuse to play nice. Solving it might require rewriting the rules of the universe or revealing deeper truths hidden in the chaos. So while black holes may seem like cosmic shredders, they could actually be the universe's most secure vaults. The catch: we don't yet know the combination. And until we do, the information paradox remains one of science's most tantalizing mysteries, a reminder that even the darkest objects in the cosmos can illuminate the deepest questions. Stephen Hawking's most revolutionary idea flipped everything we thought about black holes on its head. They aren't eternal prisons, but cosmic ice cubes slowly melting in the void. This evaporation, known as Hawking radiation, means even the universe's mightiest monsters have an expiration date. Here's how it works. At the very edge of a black hole's event horizon, quantum mechanics plays a bizarre trick. Pairs of virtual particles constantly blink in and out of existence, borrowing energy from the vacuum of space before annihilating each other. But near a black hole, something extraordinary happens. One particle gets sucked in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over billions upon billions of years, this slow leak adds up, causing the black hole to shrink until it eventually vanishes in a final burst of radiation. Now here's the catch for supermassive black holes. This process is so agonizingly slow it's practically meaningless. A typical galactic giant like Sagittarius A would take 10 to the power of 87 years, that's a 1 followed by 87 zeros, to evaporate completely. To put that in perspective, the current age of the universe is a mere 13.8 billion years. So while Hawking radiation is a fascinating theoretical quirk, it's not something we'll ever witness in real time. But for smaller black holes, the story changes dramatically. A black hole with the mass of a mountain would evaporate in less than the age of the universe, ending its life in a spectacular gamma-ray firework. Some physicists have even speculated about primordial black holes, tiny ones formed in the chaos of the Big Bang, popping like cosmic bubble wrap throughout space, their deaths emitting bursts of energy we might one day detect. What makes Hawking radiation truly mind-bending isn't just the mechanics, it's the implications. If black holes evaporate, what happens to everything they've swallowed? The information paradox we explored earlier hinges on this very question, and on an even grander scale, Hawking radiation suggests that black holes aren't just static traps. They're dynamic, evolving entities with lifespans far beyond human comprehension. They remind us that in the quantum realm, even the darkest corners of the universe can't escape the strange, shimmering rules of particle physics. So while our galaxy's central black hole isn't going anywhere, its eventual fate is written in the faint glow of particles winking in and out of existence at the edge of forever. And that's a secret written not in stone, but in the delicate dance between gravity and quantum uncertainty. In the cosmic hierarchy of black holes, there's a glaring gap, a missing link between the small stellar black holes and the supermassive giants. These intermediate mass black holes, weighing between 100 and 1 million solar masses, should be everywhere according to theory, yet they're astonishingly rare. It's like finding dinosaur fossils but no evidence of the creatures that bridge the gap between reptiles and birds. Their absence isn't just a curiosity, it's a full-blown cosmic mystery that challenges our understanding of how black holes grow and evolve. Astronomers have spotted a few tantalizing candidates. Take HLX-1, a black hole roughly 20,000 times the Sun's mass, lurking in the outskirts of a distant galaxy. Or the bizarre object in Galaxy M82, which flares with X-rays as it shreds passing stars. These rare finds suggest intermediate black holes exist, but they're the cosmic equivalent of needles in a haystack. The question is, why? If supermassive black holes grew by feasting on gas and merging with smaller ones, where are all the middleweights that should document this growth? One theory blames galactic real estate. Unlike their supermassive cousins, intermediate black holes might not have a stable home at the center of galaxies. Instead, they could wander the outskirts where food is scarce and mergers are rare. Without a steady diet of gas or stars, they stay hidden, only revealing themselves during rare feeding frenzies, like a bear hibernating deep in the woods, only spotted when it stumbles into a campsite. Another idea is that they're simply short-lived. If they form in dense star clusters through repeated collisions, they might quickly sink to the galaxy's center and merge with the supermassive black hole, leaving no trace of their existence behind. The hunt for these missing links is far from over. Gravitational wave detectors like LIGO could soon catch the ripples from intermediate black hole mergers, proving their existence beyond doubt. Meanwhile, telescopes are scanning globular clusters, ancient swarms of stars that might harbor these elusive objects. Finding them wouldn't just fill a gap in our classifications, it could rewrite the story of how the universe's most massive structures came to be. After all, every missing piece in the cosmic puzzle holds clues to secrets we haven't even dreamed of yet. Imagine a star billions of years old, dancing through its galaxy on a steady path until one wrong step sends it hurtling toward an invisible predator. As it crosses the point of no return, gravity's invisible hands grip it tighter, stretching it vertically while crushing it horizontally like cosmic taffy. This is a tidal disruption event, one of the universe's most violent and dazzling spectacles where a black hole turns a star into a temporary snack, lighting up the cosmos with a flare brighter than an entire galaxy. The violence begins long before the star reaches the event horizon. At a critical distance called the tidal radius, the black hole's gravitational pull on the star's near side becomes overwhelmingly stronger than on its far side. This difference, the tidal force, rips the star apart in a process called spaghettification. Gas from the shredded star doesn't vanish quietly. It spirals into the black hole's accretion disk, superheating to millions of degrees and unleashing a brilliant burst of X-rays, ultraviolet light, and radio waves that can outshine the star's entire lifetime in a matter of weeks. Astronomers call these outbursts TDs, and they're the closest thing we have to a black hole's dinner bell ringing across the cosmos. each event is unique, dictated by the star's size, the black hole's appetite, and even the angle of approach. A sun-like star venturing too close to a million solar mass black hole, obliterated in hours. A massive star grazing a smaller black hole, it might lose only its outer layers, surviving to orbit again, battered but not broken. Some TDs flare like matches, brightening and fading in months. Others, like at 2018, his glow for years, suggesting the black hole is savoring its meal slowly. What makes TDs more than just cosmic fireworks is what they reveal. The light from these events carries fingerprints of the star's composition, letting astronomers study elements forged in its core. The flares also map the black hole's surroundings, exposing otherwise invisible details like its spin and the structure of its accretion disk. In 2021, scientists even detected a TD spewing a jet of particles at nearly light speed, proof that black holes can turn stellar destruction into intergalactic particle accelerators. But here's the twist: not all shredded stars end up as black hole food. Some of their gas gets blown outward in fierce winds, seeding the galaxy with heavy elements that might one day form new stars or even planets. It's a paradox, destruction on a stellar scale paving the way for creation. And with observatories like the Vera Rubin scan of the sky coming online, we're on the verge of catching thousands of these events, each one a fleeting glimpse into the chaotic, dynamic relationship between stars and the monsters that lurk in the dark. So next time you hear about a sudden flare in a distant galaxy, remember, it might not be a supernova. It could be a black hole briefly stepping into the spotlight as it tears apart a star and reminds us that even in the vastness of space, gravity's appetite is never satisfied. Time doesn't tick the same everywhere in the universe, and nowhere is this more extreme than near a black hole. Einstein's theory of relativity revealed that gravity doesn't just bend space, it warps time itself, slowing clocks in strong gravitational fields. But black holes take this to another level entirely. Approach one closely enough and time doesn't just slow, it stretches like taffy, distorting reality in ways that border on science fiction. Picture two astronauts. One stays far from the black hole while the other descends toward its event horizon. To the distant observer, the approaching astronauts' movements grind to a halt, their signals stretching into slower and slower pulses. From their perspective, though, time flows normally. Minutes pass as years, decades, or even centuries elapse for the rest of the universe. This isn't just theoretical. Near Earth, GPS satellites already account for tiny time shifts caused by our planet's gravity. But near a black hole, the effect is so extreme it could theoretically allow a traveler to leap forward into the future, returning to find the universe aged millennia while they experienced mere hours. The math gets wilder when black holes spin. A rotating black hole drags spacetime around it like a whirlpool, creating what's called an ergosphere, a region where nothing can stand still, not even time. Enter this zone, and you'll be swept along in a cosmic current where past, present, and future blur. Some theories suggest that with precise maneuvers, a spacecraft could exploit this frame dragging to create closed time-like curves, loops in spacetime that might hypothetically allow travel to the past. Of course, the energy and precision required are beyond anything we could muster, and the radiation near the black hole would vaporize any known material long before such experiments could begin. Yet, even without time machines, black holes offer a glimpse into the universe's distant future. As matter spirals toward the event horizon, its light redshifts into oblivion, stretched by gravity until wavelengths become infinite. To an outside observer, the final moments before crossing the horizon are frozen in time, a last snapshot of an object that, from its own perspective, has already vanished. It's a haunting reminder that black holes don't just bend space, they rewrite the rules of cause and effect, turning the fabric of reality into a puzzle we've only begun to piece together. So while we may never harness black holes as time machines, they remain the universe's most dramatic hourglasses, places where time itself becomes fluid, and the clock ticks differently for anyone daring enough to get close. Just don't expect to come back and tell the tale. One of the most radical ideas in modern physics suggests that everything we perceive, the stars, galaxies, and even the fabric of space itself, might be nothing more than a cosmic mirage. This is the holographic principle, a theory proposing our three-dimensional universe could be encoded on a two-dimensional surface at its boundaries, like a movie projected from the edge of reality. And where does this mind-bending concept intersect with hard evidence? At the event horizons of black holes, where information about everything swallowed might not vanish but instead gets imprinted like data on a celestial hard drive. The connection starts with a puzzle we've touched on before, the black hole information paradox. If black holes truly erased information from the universe, it would violate quantum mechanics' sacred rule that information can never be destroyed. But what if the information isn't lost? The holographic principle offers a solution. Every particle, every bit of energy that falls into a black hole leaves a fingerprint on its event horizon, encoded in Planck-scale pixels far smaller than atoms. Think of it like burning a book. The pages are gone, but if you could somehow read the smoke's patterns, every word might still be there, just scrambled. Black holes aren't passive participants here. Their event horizons act as natural holograms with surface area directly tied to their entropy, a measure of hidden information. This unexpected link, discovered by physicist Jacob Bekenstein and refined by Stephen Hawking, suggests a black hole's interior might not be where the real action happens. Instead, its surface, the event horizon, could hold all the data needed to reconstruct everything inside, like a cosmic zip file, the three-dimensional space we associate with reality. Maybe just a shadow of the deeper, flatter truth. The implications stretch far beyond black holes. If the universe is holographic, then the stars above us, the planets beneath our feet, even our own thoughts, might be projections from some distant, invisible surface we can't perceive. It's as if we're living inside a simulation, but one running on the laws of physics rather than silicon chips. And black holes, with their extreme gravity and quantum quirks, are the universe's way of revealing the stitching in this cosmic tapestry. Here's where it gets wilder. Some versions of string theory suggest that our entire universe could be a hologram projected from the edge of a higher dimensional space, with black holes serving as cosmic pixels where the encoding is most visible. Experiments with quantum gravity simulations and lab-created analog black holes are already testing these ideas, hunting for glitches in reality's projection. If confirmed, it would mean that the most destructive objects in the cosmos are also the universe's most meticulous librarians, safeguarding information in a form we're only beginning to decipher. So while black holes may seem like endpoints, they could actually be gateways not to other places, but to a deeper understanding of reality itself. The next time you gaze at the night sky, consider this: the darkness between the stars might not be empty. It could be a vast, shimmering screen, and black holes the projectors casting the cosmic movie we call existence. Somewhere in the depths of space, two supermassive black holes, each weighing billions of suns, circle each other in a silent, deadly dance. They don't collide immediately. Instead, they spiral closer over millions of years, their immense gravity stirring the fabric of space-time like spoons in cosmic honey. Then, in one cataclysmic moment, they merge, releasing more energy than all the stars in the observable universe combined. But here's the astonishing part: we can't see it happen. There's no flash of light, no explosion to mark the event. Instead, the collision sends invisible ripples racing outward at the speed of light. Gravitational waves, the universe's most subtle yet powerful messengers. Einstein predicted these ripples over a century ago, but it wasn't until 2015 that humanity first detected them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faint tremor from two smaller stellar mass black holes colliding. The signal was tiny, a distortion smaller than an atom's width, but it proved gravitational waves were real. Now, imagine that same phenomenon scaled up to supermassive proportions. When black holes this big merge, their gravitational waves aren't whispers. They're cosmic thunderclaps shaking space-time itself with frequencies so low they vibrate once every few hours or days. Detecting these deep space tremors requires entirely new technology. Ground-based observatories like LIGO can't catch these ultra-low frequencies. Their arms are too short. That's where space missions like LISA come in. Scheduled to launch in the 2030s, the Laser Interferometer Space Antenna will float 3 spacecraft millions of kilometers apart, linked by lasers precise enough to measure movements a fraction of an atom's width. This space-based ear will tune into the universe's deepest, slowest vibrations, the echoes of black holes merging in galaxy cores across the cosmos. What's truly wild is how these waves encode information. Each ripple tells the story of the collision, the black hole's masses, spins, even how they formed. Some waves might reveal if supermassive black holes grew by gobbling up smaller ones or feasting on gas. Others could hint at exotic possibilities, like black holes born from the Big Bang itself. And in rare cases, if the merger happens just right, the resulting black hole might get kicked away at incredible speeds, a gravitational recoil so strong it flings the monster clear of its galaxy. But gravitational waves aren't just about black holes. They're reshaping our view of the universe. Every merger we detect is like adding another piece to a cosmic jigsaw puzzle, revealing how galaxies evolve, how matter clusters, and perhaps even secrets about dark energy. Future observatories could catch the moment when the very first supermassive black holes formed, giving us a glimpse into the universe's chaotic infancy. So while we can't see these collisions directly, the waves they leave behind are like fingerprints on space-time, silent, invisible but packed with stories. And as our technology improves, we're learning to listen, turning the faintest tremors into a symphony of the cosmos' most violent, majestic events. Ton 618 isn't just a black hole, it's a cosmic anomaly so colossal it redefines the limits of what we thought possible. Clocking in at 66 billion times the mass of our Sun, this behemoth dwarfs even the supermassive black holes anchoring most galaxies. To put that into perspective, if you replaced our Sun with Ton 618, its event horizon would stretch far beyond Pluto's orbit, engulfing our entire solar system like a gravitational tsunami. Yet the real mystery isn't just its size. It's how something this massive could exist at all in a universe that's only 13.8 billion years old. Most supermassive black holes grow by feasting on gas, merging with others, or absorbing stars over eons. But Ton 618's appetite would have needed to defy physics as we know it. Even if it devoured a sun's worth of material every single day since the Big Bang, it still wouldn't have reached its current size. This glaring mismatch has forced astronomers to rethink black hole formation entirely. Could it have been born from a direct collapse of primordial gas clouds in the early universe, bypassing the usual star-first route? Or does it hint at exotic physics like black holes feeding on dark matter or merging in hyper-dense cosmic environments we've yet to observe? What makes Ton 618 even stranger is its host, a blazar, a galaxy with a jet of particles pointed almost directly at Earth. This quasar's light has traveled over 10 billion years to reach us, meaning we're seeing it as it existed when the universe was just a quarter of its current age. That raises another puzzle. How did it grow so unfathomably large so quickly? Recent simulations suggest the early universe might have been a black hole breeding ground, with dense regions of gas collapsing directly into giants without the need for stellar precursors. Yet even these models strain to explain Ton 618's sheer scale. And then there's the light. Ton 618's accretion disk is the brightest known object in the universe, outshining entire galaxies. If it were placed where our Milky Way's black hole sits, its glow would outshine the full moon in our night sky, casting shadows on Earth. That radiant fury isn't just spectacle, it's a clue. The disk's emissions let astronomers map the black hole's spin, magnetic fields, and even the way it warps space-time. Yet for all its brilliance, TON 618 remains elusive. We've never directly imaged it, and its distance makes detailed study a challenge. This record holder is more than a curiosity, it's a boundary pusher. Its existence forces us to confront gaps in our understanding of cosmic growth, the nature of quasars, and the wild diversity of black holes. Some theories even speculate that TON 618 might not be alone, that an entire class of ultra-massive black holes lurks in the cosmic shadows, waiting to upend our theories once more. Until then, this titan stands as a reminder that the universe loves breaking its own rules, and the biggest monsters often hold the deepest secrets. Dark matter makes up 85% of the universe's mass, yet it refuses to interact with light, slipping through our detectors like a cosmic ghost. But what if black holes, the universe's ultimate gravitational traps, hold the key to finally revealing dark matter's secrets? The connection between these two cosmic enigmas sparks some of astrophysics' most thrilling possibilities. Imagine dark matter particles swirling around a black hole's event horizon, caught in its gravitational web without ever emitting a single photon. While ordinary matter heats up and shines in an accretion disk, dark matter would silently accumulate, invisibly fattening the black hole over eons. This isn't just speculation, it could solve long-standing mysteries. Take those impossibly massive early universe black holes like TON 618. How did they grow so big so fast? One theory suggests they feasted on dark matter, an all-you-can-eat buffet of invisible particles that would explain their rapid growth without requiring unrealistic amounts of ordinary gas. Unlike normal matter, which gets heated and ejected in fiery jets, dark matter would plunge directly into the black hole, vanishing without a trace except for the black hole's sudden, inexplicable weight gain. The dance between dark matter and black holes might leave other subtle clues. Some models predict dark matter forms dense spikes around black holes, creating gravitational footprints detectable in the orbits of nearby stars. Others suggest merging black holes could fling dark matter particles outward like cosmic slingshots, leaving faint imprints in gravitational wave data. There's even the wild idea that primordial black holes, tiny ones forged in the Big Bang, are dark matter, their collective gravity shaping galaxies without ever being seen. Yet the most tantalizing possibility is annihilation. If certain dark matter particles collide near a black hole's intense gravity, they could explode into gamma rays, a faint but telltale signature. Telescopes are already scouring the skies for these flashes, hunting for proof of this invisible partnership. And if they find it, it would rewrite our understanding of both dark matter's nature and black holes' hidden appetites. So while dark matter remains elusive, black holes might be the universe's backdoor, a way to study something invisible by watching how it bends the darkest objects we know. The next breakthrough in this cosmic detective story could come from a black hole's silent feast, revealing secrets hidden since the dawn of time. Rising like ghostly towers above the Milky Way's disk, two colossal orbs of gamma-ray light stretch 25,000 light-years into the void, one north, one south, like a cosmic hourglass frozen in time. These are the Fermi bubbles, a pair of violent remnants from our galaxy's ancient past, and they whisper a startling secret. Sagittarius A, the sleeping giant at our galaxy's heart, was once a raging monster. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these bubbles glow with high-energy radiation, their edges razor-sharp against the darkness. Their sheer scale is staggering enough to swallow 25,000 solar systems lined end to end. But what carved them? The leading theory points to a cataclysmic outburst from Sagittarius A between 2 and 4 million years ago, when it briefly transformed from a quiet recluse into a quasar-like beast. Imagine our black hole belching out twin jets of superheated plasma at nearly light speed, punching through the galaxy's gas like cosmic blowtorches and inflating these immense lobes. The evidence doesn't stop at gamma rays. The bubble's bases align perfectly with Sagittarius A, and their composition, superheated gas laced with heavy elements, matches what astronomers expect from black hole jets. Even more telling, the southern bubble flickers with X-rays in a pattern that mirrors the black hole's spin axis, like a fossilized echo of its ancient fury. And here's the kicker: studies of the Magellanic Stream, a river of gas wrapping around our galaxy, show scorch marks from an energy surge timed to the bubble's formation. It's as if we're seeing the aftermath of a galactic-scale explosion, one that heated gas across hundreds of thousands of light years. Yet this wasn't a one-time event. Sagittarius A likely erupts in cycles, feasting then fasting over eons. Each outburst could reshape the galaxy, blowing away star-forming gas or triggering new stellar births in its wake. And while we've caught it napping for now, the Fermi bubbles are a stark reminder. Even the quietest black holes have violent pasts and explosive futures. One day, perhaps millions of years from now, our silent sentinel will wake again, and the Milky Way skies will blaze with light we can scarcely imagine. Capturing the shadow of a black hole, an object so dense that light itself can't escape, sounds like an impossible task. Yet in April 2019, humanity did just that. The Event Horizon Telescope, a planet-sized array of radio observatories spanning the globe, unveiled the first ever image of a black hole silhouette nestled in the heart of galaxy M87. This wasn't just a blurry smudge on a screen. It was a triumph of science, engineering, and sheer human perseverance, revealing the invisible in a way that even Einstein might have found unbelievable. The key to this breakthrough wasn't a single telescope, but a network of 8 observatories synchronized to act as one. By combining radio dishes from the icy peaks of the South Pole to the high deserts of Chile, astronomers created a virtual telescope as wide as Earth itself, a technique called very long baseline interferometry. The resolution achieved was so sharp it could spot a donut on the moon while standing on Earth. But even with this technological marvel, the team faced a daunting challenge. Black holes don't emit light. Instead, the image captures the shadow cast by the black hole against the glowing plasma of its accretion disk, a dark void ringed by a fiery halo of superheated gas bending around it like a cosmic lens. Processing the data was another Herculean feat. The telescopes gathered so much raw information equivalent to streaming 40,000 Netflix movies that it couldn't be sent over the internet. Hard drives had to be physically flown to supercomputers in Germany and Massachusetts, where algorithms painstakingly stitched together the signals. The final image, refined over years, matched predictions from Einstein's general relativity with eerie precision, confirming that the black hole's shadow was shaped exactly as spacetime's warping should dictate. What makes this shadow so revealing? Its asymmetry holds clues to the black hole's spin, while the brightness asymmetry in the ring hints at relativistic effects like Doppler beaming, where material moving toward us appears brighter due to its mind-bending velocity. Even the shadow's size, about 2.5 times larger than the event horizon, serves as a cosmic ruler, allowing astronomers to calculate M87's black hole mass at 6.5 billion suns. But this breakthrough was just the beginning. In 2022, the HT turned its gaze toward Sagittarius A star, our Milky Way's own supermassive black hole, producing another eerie ring, this time smaller and more turbulent, reflecting our galaxy's quieter but no less fascinating giant. Future upgrades, including space-based antennas, could sharpen these images further, potentially revealing the magnetic fields twisting around black holes or even the mysterious photon ring, where light orbits the black hole multiple times before escaping. So while black holes remain the universe's ultimate paradoxes, both simple in theory and infinitely complex in detail, their shadows have become our windows into the extreme. That first image was more than a scientific milestone. It was humanity staring into the abyss and finding, against all odds, that the abyss stared back with a glowing golden ring. At first glance, black holes seem impossibly complex cosmic shredders where gravity twists space and time into knots, where matter vanishes without a trace, and where the laws of physics themselves break down. Yet hidden in this chaos is one of the universe's most elegant surprises. Black holes might be the simplest objects in existence. This counterintuitive idea is captured by the no-hair theorem, a concept so poetic in its simplicity that it reduces these gravitational monsters down to just three bare essentials: mass, spin, and charge. The name itself is a playful metaphor. Just as a haircut can't change who you fundamentally are, a black hole's hair represents all the extra details: what fell into it, how it formed, the type of matter it consumed. According to the theorem, none of that matters once material crosses the event horizon. Whether a black hole devours a star, a planet, or an entire spaceship, all that remains in its gravitational fingerprint are those three properties. Mass determines how strongly it warps space-time, spin reveals how it drags the fabric of reality around it, and charge, though rare in practice, hints at electromagnetic quirks. Everything else erased as if the universe hit a cosmic reset button. This radical simplicity emerges from the math of general relativity. When matter vanishes into a black hole, its information isn't just hidden, it's fundamentally inaccessible to the outside universe. There's no way to tell if the black hole formed from a collapsed star or 1,000 planets. Its gravitational pull and effects on space-time depend only on those three numbers. Even wilder, two black holes with identical mass, spin, and charge are completely indistinguishable, no matter their history. It's like meeting two people who look identical, sound identical, and move identically, except one grew up on Earth and the other in a distant galaxy. But here's where things get thorny. The no-hair theorem clashes with quantum mechanics, which insists information can't be destroyed. If black holes truly erase everything but those three details, they're violating one of physics' most sacred rules. This tension fuels the black hole information paradox we explored earlier, with some theorists suggesting the hair might still exist, just scrambled into quantum patterns on the event horizon. Others propose subtle deviations, tiny gravitational imprints called soft hair, that could preserve traces of what fell in. Despite these debates, the theorem holds profound implications. It means black holes, for all their terrifying power, are cosmic blank slates, predictable, calculable, and eerily uniform. Their simplicity is why we can simulate them with equations, image their shadows, and study their collisions through gravitational waves. They might be the universe's way of reminding us that beneath the chaos, the deepest truths are often the most elegant. So while black holes appear monstrous, they're really just cosmic tombstones with three-word epitaphs: mass, spin, and charge. The rest, as far as the universe is concerned, is just noise. Black holes might be cosmic dead ends, but what if they hide secret passageways, enter wormholes, the hypothetical tunnels through space-time that have fueled science fiction dreams for decades? While black holes famously let nothing escape, wormholes promise shortcuts across the universe, bridges connecting distant points that could, in theory, allow near-instantaneous travel. The twist: these cosmic portals might not be so different from their destructive cousins. Some theories suggest that under the right conditions, a supermassive black hole's extreme gravity could twist space-time so severely that it pinches into a tunnel, linking one point in the cosmos to another like a celestial subway. The key difference lies in stability. A typical black hole's singularity, a point of infinite density, would shred anything attempting to pass through. But certain solutions to Einstein's equations hint that a spinning black hole might harbor a different kind of core, a ring-shaped singularity that could hypothetically act as a gateway rather than a shredder. Picture diving into a black hole's swirling depths only to emerge light years away, with the event horizon serving as the entrance to a cosmic corridor rather than a one-way trip to oblivion. There's just one catch: wormholes, if they exist at all, would likely collapse instantly without some form of exotic matter to prop them open. This hypothetical substance would need negative energy, counteracting gravity's crushing force long enough for anything to traverse the tunnel. Nobody knows if such matter exists, but quantum physics offers tantalizing clues. Microscopic wormholes might flicker in and out of existence at the Planck scale, woven into the quantum foam of spacetime itself. Could a supermassive black hole's immense energy stabilize one of these fleeting tunnels? It's a long shot, but not impossible. Even wilder is the possibility that some quasars or active galactic nuclei aren't just black holes at all, but the luminous mouths of wormholes. Their relativistic jets and bizarre light curves could, in theory, match the predicted signatures of a traversable tunnel's throat. Observations of odd cosmic flares, like one recently spotted in galaxy SDSS-J 1430, have even sparked debates over whether we've already glimpsed these structures without realizing it. Of course, for now, wormholes remain firmly in the realm of speculation, but the fact that they emerge naturally from relativity's math suggests the universe might play by rules stranger than fiction. And if black holes truly can warp spacetime into bridges, then the most terrifying objects in the cosmos could also be its most revolutionary, turning monsters into architects of interstellar highways. Until then, they remain the ultimate what-if, teasing us with the possibility that somewhere in the abyss, a shortcut through the stars might be waiting. What if black holes weren't just cosmic monsters, but the ultimate power plants for civilizations far beyond our own? This isn't just science fiction. Cutting-edge physics suggests that advanced beings could theoretically drain energy from these gravitational behemoths, turning them into batteries capable of fueling interstellar empires. The idea hinges on one of the universe's most mind-bending phenomena: the ergosphere, the region outside a spinning black hole's event horizon where spacetime itself gets dragged around like water in a whirlpool. Here, the rotational energy is so vast that tapping into just a fraction could power entire worlds. The key lies in something called the Penrose process. Imagine dropping an object into the ergosphere, a spacecraft, or even just a chunk of matter, then splitting it in two. One piece plunges into the black hole, but the other gets flung outward with more energy than it started with. It sounds like magic, but it's pure physics. The black hole's spin transfers energy to the escaping fragment, effectively siphoning power from the void. The numbers are staggering. A rapidly spinning supermassive black hole could theoretically yield up to 20% of its total mass as usable energy. For comparison, nuclear fusion, the sun's power source, converts less than 1% of mass into energy. But why stop there? Enter the Dyson-Harrop satellite, a hypothetical megastructure that could harvest energy from a black hole's relativistic jets. These plasma beams pouring out the poles of feeding black holes carry enough power to outshine galaxies. A civilization advanced enough to build collectors in their path could harness energy on a scale we can barely fathom. Some models even suggest using the black hole's accretion disk as a mirror, bouncing lasers off its superheated plasma to generate electricity far more efficiently than any solar panel. The wildest proposal, quantum energy extraction. Near the event horizon, virtual particles constantly blink in and out of existence, the same phenomenon behind Hawking radiation. A sufficiently advanced society might deploy quantum scoops to capture these particles before they annihilate, converting their energy into usable power. It's the ultimate recycling program, turning spacetime's quantum fuzz into a boundless energy source. Of course, the engineering challenges are astronomical. stabilizing orbits near the event horizon, surviving lethal radiation, and building structures on scales dwarfing planets. These aren't hurdles our species will overcome anytime soon. But for a Type 3 civilization, one that's mastered energy at a galactic level, black holes wouldn't just be gravitational anchors. They'd be the ultimate renewable resource, offering near-infinite energy long after stars burn out. So while we're still stuck burning fossil fuels somewhere in the cosmos, a hyper-advanced society might already be plugging into the darkness, turning the universe's most destructive force into the foundation of their utopia. Quasars don't just shine, they scream. These dazzling beacons, the brightest objects in the cosmos, are more than distant curiosities. They're the universe's way of turning supermassive black holes into celestial lighthouses. At their core lies a paradox: the darkest objects in existence, powered by gravity so strong light can't escape, somehow illuminating the cosmos with radiation that outshines entire galaxies. The secret: chaos. When a supermassive black hole gorges on gas, dust, and stars, the material doesn't vanish quietly. Instead, it's funneled into a swirling accretion disk, heated to millions of degrees by friction and magnetic turbulence until it glows with the fury of a trillion suns. But quasars aren't just cosmic blowtorches, they're time machines. Because light takes time to travel, the farther we peer into space, the further back in time we see. The most distant quasars detected existed when the universe was less than 1 billion years old, their light stretching across 12 billion years before reaching our telescopes. That means their central black holes, some weighing billions of solar masses, had to form and grow to staggering sizes impossibly fast. Traditional models of black hole growth can't explain this speed, forcing astronomers to consider wild alternatives like direct collapsing primordial gas clouds or black holes born already massive from the Big Bang's chaos. What makes quasars even more valuable is their uniformity. No matter their distance or host galaxy, their light follows predictable patterns, allowing scientists to use them as cosmic yardsticks. By analyzing the subtle shifts in their spectra, the fingerprints of elements like hydrogen, helium, and carbon, astronomers can map the universe's expansion, measure the density of intergalactic gas, and even probe the nature of dark energy. Some quasars flicker in brightness over days, revealing details about the accretion disk structure, while others show polarized light, hinting at the magnetic fields twisting near the event horizon. Then there's their role as galactic sculptors. The energy unleashed by a quasar doesn't just vanish into space, it slams into surrounding gas clouds, heating them so intensely that star formation shuts down across entire regions. This feedback mechanism explains why some massive galaxies are red and dead, their stellar nurseries extinguished by black hole outbursts billions of years ago. Yet in a twist of cosmic irony, the same jets that sterilize galaxies also seed them. Quasars spew heavy elements forged in their accretion disks, sprinkling the cosmos with the raw ingredients for planets and life. So while quasars may seem like relics of a violent past, they're far from extinct. Every supermassive black hole, including our Milky Way's quiet Sagittarius A, has the potential to awaken as a quasar if given enough fuel. And when they do, their light will cut through the darkness once more, etching new chapters in the story of the universe, one brilliant, ravenous flash at a time. Once matter crosses a black hole's event horizon, it enters a realm where the known laws of physics dissolve into paradox. The equations of general relativity predict an inevitable journey toward the singularity, a point of infinite density where space and time cease to exist as we understand them. But here's the catch: infinity isn't a physical state, it's a mathematical warning that our theories have hit a wall. Beyond the horizon, the fate of swallowed matter isn't just mysterious, it's a battleground for the greatest unsolved conflict in physics: the clash between Einstein's relativity and the quantum world. Consider a star plunging into the abyss. From an outsider's perspective, it freezes at the horizon, its light red shifting into oblivion. Yet from the star's own reference frame, it crosses the threshold unimpeded, torn apart by tidal forces as it falls toward the singularity. This duality hints at a deeper truth. Black holes aren't just objects but laboratories for testing the union of the very large and the very small. At the singularity, gravity becomes so intense that quantum effects, normally negligible on cosmic scales, can no longer be ignored. The smooth spacetime of relativity shatters into a froth of probabilistic fluctuations, where dimensions twist and particles blink in and out of existence. This is where string theory and loop quantum gravity step in, proposing radical alternatives to the singularity's infinities. String theory suggests matter might be transmuted into vibrating strands of energy, while loop quantum gravity imagines a woven fabric of spacetime that resists infinite collapse. Some models even replace the singularity with a Planck star, a dense but finite remnant where matter rebounds in a quantum bounce. These ideas remain speculative, but they share a thrilling premise. The black hole's interior isn't an endpoint but a gateway to new physics. The stakes couldn't be higher. If quantum gravity governs the core, it could rewrite our understanding of information, entropy, and even the nature of time itself. Hawking radiation hints that black holes preserve information in scrambled form, encoded on their horizons like holograms. But what happens to that information inside? Does it linger in some higher dimensional structure, or is it truly erased, violating quantum mechanics' sacred laws? The answer might lie in the firewalls controversy, a proposition that the horizon is a searing wall of energy, annihilating anything that touches it. Yet perhaps the most poetic possibility is that matter doesn't vanish at all. In some theories, black holes are cosmic alchemists, transforming stars and gas into exotic states of energy that could tunnel into other universes or birth new ones. The singularity might not be a grave but a crucible, forging realities we can't yet imagine. Until we bridge relativity and quantum mechanics, the black hole's heart remains the ultimate enigma, a place where matter doesn't die but becomes something stranger than fiction. What if our universe isn't alone and black holes are the hidden tunnels stitching reality together? The idea of a multiverse, a vast cosmic tapestry of parallel realities, has long captivated scientists and storytellers alike. But supermassive black holes, with their spacetime warping gravity, might be more than just galactic anchors. They could be the universe's architects, weaving connections between worlds we can't yet see. Start with the mathematics. Einstein's equations allow for the existence of wormholes, bridges between distant points in space-time, though they're often dismissed as requiring exotic matter to stay open. Yet spinning supermassive black holes with their ergospheres and ring-shaped singularities flirt with these very possibilities. Their extreme rotation could twist spacetime so severely that it folds, creating shortcuts to other regions or even other universes. Some theories propose that what we perceive as a black hole's singularity might actually be a gateway, a cosmic toll booth where matter gets funneled into a new reality with its own laws of physics. Then there's the holographic principle's wild implication. If our universe's information is encoded on a two-dimensional boundary, like a black hole's event horizon, could that boundary itself be the gateway to something larger? Picture a supermassive black hole as a pixel in a grander cosmic code, its surface holding not just the data of what falls in, but a hidden key to alternate dimensions. This isn't pure fantasy. String theory calculations suggest higher dimensional spaces where black holes serve as anchors, their gravitational pull tethering our universe to others in an invisible web. But the most tantalizing clues come from quantum mechanics. When particles vanish into a black hole, where does their information go? The many worlds interpretation offers a radical answer. Perhaps it doesn't vanish at all. Instead, it branches off, spawning new universes where every possible outcome of quantum uncertainty becomes reality. In this view, supermassive black holes aren't endpoints. their cosmic tree roots sprouting new branches of the multiverse with every star they consume. Of course, evidence remains elusive. Wormholes, if they exist, would likely collapse instantly without negative energy, a substance we've never observed. And the multiverse, for all its mathematical elegance, is notoriously hard to test. Yet black holes keep nudging us toward these possibilities. Their singularities defy physics as we know it. Their event horizons scramble information in ways that hint at deeper layers, and their sheer existence challenges our understanding of reality's fabric. So while we can't yet peer beyond the event horizon, its shadow might hold more than darkness. It could be a reflection of infinite worlds, each twisted into existence by the same gravity that makes black holes the universe's most enigmatic architects. Until the day we unlock their secrets, they'll remain both monsters and messengers whispering that our cosmos might be far stranger and far more connected than we ever dreamed. In the unimaginably distant future, when the universe has stretched into a cold, dark wasteland, supermassive black holes may be the last beacons in the void, silent titans outliving stars, galaxies, and even light itself. As the cosmos expands relentlessly, accelerating under the mysterious influence of dark energy, clusters of galaxies will vanish beyond each other's horizons, leaving isolated islands of matter adrift in an ever-growing emptiness. Stars will burn out, their remnants drifting apart, and even the stubborn white dwarfs and neutron stars will eventually fade into quantum froth, but black holes. These cosmic survivors will persist, their gravitational grip unshaken by the universe's slow demise. Yet even they aren't immortal. Thanks to Hawking radiation, the slow quantum leak at their event horizons, black holes will eventually evaporate, but on timelines so vast they make the current age of the universe seem like a blink. For a typical supermassive black hole, this process could take 10 to the 100th power years, a 1 followed by 100 zeros. To put that in perspective, if you wrote out this number in seconds, it would dwarf the current age of the universe by more orders of magnitude than there are atoms in the observable cosmos. During this unfathomable twilight era, black holes won't just fade quietly. As they shrink, their evaporation accelerates, culminating in a final, dazzling burst of gamma rays, a last whisper of energy marking their departure from reality. The largest black holes, like Ton 618, might even outlast the protons that make up all matter, surviving long enough to witness the decay of atoms themselves. Some theories suggest that in this era, the universe will consist of nothing but these fading black holes and a sea of subatomic particles spread so thin that distances between them are measured in light years. But here's the twist: their deaths might not be the end. Some speculative models propose that evaporating black holes could birth new universes in their final moments, their singularities birthing new big bangs in a hidden pocket of spacetime. It's a poetic symmetry, the last remnants of our cosmos becoming the seeds for new realities, their physics entirely different from ours. Others suggest that if any advanced civilizations still exist, they might harness these dying giants as their last energy sources, riding the Hawking radiation until the final flicker. So while today's black holes are the universe's most destructive forces, in the far future, they could become its last monuments, lonely sentinels of a once vibrant cosmos, and perhaps the quiet architects of whatever comes next. From the violent births of supermassive black holes in the early universe to their potential role as cosmic gateways to other dimensions, we've journeyed through 30 astonishing secrets that reveal these gravitational monsters as the universe's ultimate paradoxes, destroyers and creators, time warps and information vaults, cosmic architects and potential energy sources for civilization. Can't yet imagine. We've seen how they spin space itself like taffy, how they launch jets of matter at nearly light speed, and how they might hold the key to uniting relativity with quantum mechanics. Yet for every mystery solved, like the glowing rings captured by the Event Horizon telescope, dozens more remain. Why do some black holes flare unpredictably while others slumber for eons? How do they influence dark matter's invisible web? And what truly happens beyond the event horizon? Do singularities rewrite physics, or do wormholes wait in the darkness? The most thrilling revelation isn't any single fact, but the overwhelming truth that we've barely scratched the surface. Each breakthrough peels back another layer, revealing deeper questions hidden beneath. Astronomers are now hunting for intermediate mass black holes to fill the cosmic gap, listening for gravitational waves from ancient collisions, and probing whether Hawking radiation could one day unveil quantum gravity's secrets. Meanwhile, simulations push the limits of what we think possible, from holographic universes encoded on black hole surfaces to the wild possibility that these objects might be cosmic recyclers, birthing new realities in their depths. That's the real magic of black holes. They're not just celestial oddities, but cosmic teachers. Every discovery about them reshapes our understanding of space, time, and the fundamental laws governing existence. So stay curious, because the next chapter in this story could rewrite textbooks overnight. If you've enjoyed this dive into the abyss, hit subscribe to explore more cosmic mysteries, from dark energy's grip on the universe to the search for alien megastructures. And drop your favorite black hole fact in the comments below. Was it the spaghettification of stars, the time-warping spin of Kerr black holes, or the mind-bending holographic principle? The universe is full of wonders, and the conversation is just beginning.